Awesome. Hello, everybody. So my name is Gamarro, and I am a PhD major in mechanical engineering at the City College of New York. And I am also currently, I think it's one of the first class of the NOAA Graduate Fellowship Program. And I am very excited to present, and those two presentations before were awesome. So thank you very much. So today I'll be talking about some of the work that I'm currently doing, trying to model the urban impacts in air quality forecasting. And a lot of this work is in collaboration with the Chemical Sciences Lab in Boulder, Colorado with Dr. Brian McDonald. So the main reason why I focus on this problem is because I live in New York City, and one of the main issues is it gets very hot in the city. And it's interesting to understand these urban dynamics and how they impact the model, because a lot of times these models don't really take into account the complexity of how the urban system works in the model. And so the key science questions that I'm trying to tackle are, does urban dynamics affect the distribution of air pollution? And to what extent does the land-ocean thermal gradient affect this coast? And for me, the main case study that I was interested in happened during this big field campaign called Listos Field Campaign. And during this event on July 2nd, 2018, there was a heat wave event that occurred, and you had a very high increase in ozone, and that's demonstrated in these slides. And so the proposed method to tackle this question, to see how we can take into account the urban dynamics in the model, was to configure a weather model. It's called WRF, Weather Research and Forecasting Model, and introduce this multi-layer urban canopy parameterization, which is a set of code that that's built to try to take into account this urban canopy dimension. And so I'll show you a figure in the upcoming slides. And so when I say weather forecasting model, this is essentially how we configured it, and we used WRF over this domain. So the domain 1 covers all of CONUS, and we target the East Coast in the domain 2. And for this case study, what we did was we took these urban canopy codes and turned it on, and then we turned it off. And a lot of these models are driven by the NAM meteorology. We also worked a lot to try to improve some of the emission sources for the chemical side of the code. And that's where collaboration with the Chemical Sciences Lab really helped, because they do a lot of the state-of-the-art work to improve that process. And a lot of that discussion is given by my mentor, Brian McDonald, in his papers. And so I mentioned this urban canopy scheme a few times already. This is what I mean. With this code, what we do is we take into account how the building environment works in the model, and it's all parameterized in the land surface schemes of these weather models. And this figure is a really good representation of what happens in the code. A lot of the times in the land surface model, you don't take into account how these buildings affect momentum or turbulence or the heat. And so we parameterize those processes and put them in the code. And another interesting part with that code is we also have a building energy model. So when it gets really hot, you have a feedback loop where the buildings turn on the air conditioner, but then a lot of the anthropogenic heat escapes. And so that mechanism is also built into the model. So here, for the two cases, I took the city off case, which is top my right, and city on. And the hard part with these models in trying to introduce the urban setup is you need a way to describe how the buildings are distributed in the city. And so one of my main tasks with working at the Chemical Sciences Lab is to try to take the work that we do in New York and expand it to all the cities. One key point that I do want to make is running these codes are very expensive in terms of computation. And so for meteorology, there still needs some steps to make it, to add it to the actual operational forecast. But when you're talking about chemical modeling is already very expensive. So adding the urban part to it doesn't contribute too much computational speed up. So we're targeting that first, and then trying to see later on if we can improve the processes to include it in the general MET forecast. So here are my first results, and although the thing is covering, here are just two stations in the city. So one is the Bronx and one is Brooklyn. And I just want to highlight that if you look at the statistics, the urban honors, in this case is doing better, tackling the peaks, but there still needs to be some work done for the nighttime, which is hard for both models in general to capture what happens at night. But I believe more tuning would get the urban on peak lower to match what happens at night. I expanded to two stations a little bit outside of the city, but they still do have some representation of the urban. And for the urban on case in blue, you did see better representation at night and then the peak. Here, what I'm showing is a temperature distribution of the model for two key times at 6 in the morning and at 7 in the morning. And the way I have these figures set up is my ultimate right is the city off case, in the middle is the city on case, and then to the right, to my left is the observations. And some key points that I want to make are the urban heat island at the morning at 6 was better represented for the city on case, whereas in the city off, it wasn't. And then at 7, here was when the sea breeze started creeping up and a regional heating dominated the event, which ultimately led to this high peak in a few hours. So what I want to show here is the sea breeze front development at 8 and at 9. And these sea breeze fronts were drawn using the surface temperature. I also looked at how the winds changed. And what I'm showing here is what happened at 8 and what happened at 9. And at 8, you do see the accelerated flow due to the impacts of the city. And then at 9 is when it reached the city. At 11 and 12, here you see that the sea breeze front stalled a little bit once it reached the city, which for me was nice because I added the building, so that's what I wanted to see. And then at 12 was when both the sea breeze front passed over the city. And so going to now from meteorology to chemistry, the first thing that I was interested in looking at was to see how it affects NO2, which is the precursor for ozone. And for me, one of the interesting things that happened during this campaign was there was a series of flights that occurred over the city where they took an instrument called geotassel to try to see how the NO2 column was distributed over the city. And for me, when I was thinking of the project for NOAA, this is an interesting result because as we move forward, NOAA is interested in adding more capabilities for NO2 in terms of satellite networks. For example, Tropomi right now is great because you get a distribution, but you only get it twice or once a day. Whereas future work is to try to get this type of data but on a more consistent 5-minute basis. And so we think that this will improve a lot of the modeling efforts. So here, what I'm showing is on the top is the AM flight, and then the bottom is the PM flight of NO2 column. And on the urban off case, what's interesting is it's not as, the magnitude is not as strong as the urban on case, where we saw some of the convergence into the city, which I forgot to mention, but there was some convergence into the city that happened in the morning, which built up that NO2. And the magnitude is showed on the urban on case, which matches what the observation was showing. For the PM flight, the urban off case had a much lower reduced magnitude versus the urban on case, which highlights the fact that you do need to include these cities to try to capture how the stalling effect of the city occurs and how the thermal gradients like the sea breeze effect occur. And finally, what I'm showing here is the surface ozone distribution for the event. And at 12, that's when the sea breeze just passed. And then at 14 is where you had the biggest concentration of NO2. And from here, for me, what's very interesting is how on the city off case, the distribution is more narrow over the Hudson River Valley, whereas in the city on case, it's more distributed across. And you also have a little bit of the lingering towards the bottom coast of Long Island. And so modeling ozone with the city, and this is at 4 kilometers, it's very hard. So there is a lot of work that still needs to be done, but I feel like there's promising results. And here I have some a time series plot at Mount Ivy, New York, which is close to the peak over the Hudson River Valley on the top. And then CCNY is right in the middle of the city. And one thing that I am, that's also promising is how ozone affects in the nighttime, which is also very hard due to what happens with the planetary boundary layer physics and a lot of what is like the urban heat island effect. What I'm showing here now to end my results is just a first step table of comparing it with stations. And what I have highlighted in the green is where the urban on model did better, and then everywhere else, it's a little bit hard to see here, but one thing that I am working on is to break this up into more like what happened in the night and how are the statistics in the night, what happens in the day and what are the statistics in the day. Yeah, so to conclude, I do feel like including these urban canopy parameterizations are important. Although the speed for these computations take on, tackling it with chemistry is, for me, I believe is a good first step so we can improve the code later on. And to some of my future work is to do more temperature and wind and break it up into groups. I also have the good New York Mesonet network where they have a lot of microwave radiometers. They have a lot of LiDARs all across the state. So I will try to incorporate that into my analysis. And then another thing is look at tropomi and use that NO2 column and compare it with the model. So thank you very much, and yeah, thank you.
Yeah, very interesting work. And you mentioned something at the end that made me think, I know you're partitioning kind of between day and night, but are you looking at any data that happens at that transition, like early morning when you get boundary layer kind of spinning up and developing, and then in the evening as things change? Are you looking at those two kind of very dynamic periods within the 24 hours?
Yeah, so what I showed was more of surface station evaluation, but that's where including the LiDAR and wind and the microwave radiometer at, they have inside New York City, they have about 3 stations, including CCNY, so you got 4. And so from there, I think I could really hone in on that transition on a vertical level and figure out what happened. And it's true because the PDL dynamics is one of the hardest things to get in the model. And there's been a lot of work to improve, especially MYNN with Joe Olson. Some of the one person in my group worked with Joe Olson, adding the urban component to the MYNN PDLC, and the MYNN is what NOAA uses. And so hopefully, yeah, definitely looking into that transition zone, I think is important.
Yeah, what you mentioned about the chemical aerosol mechanism you use. And the other thing is, if you use MYNN scheme, probably the Joe Olson's cloud scheme is not hooked up with photolysis, which can actually make a big difference. To my check into cloud comparison, this actually would be really a really nice thing if you have that available. Yeah.
So in terms of the chemical schemes, I used the RACM 2. In terms of aerosols, I would have to get back on you. And for the comments on the MYNN scheme, yeah, I know Joe Olson worked a lot on including the cloud representation in his newest release. And clouds are also very hard. Yeah, I will definitely look into it.
All right, we'll go one more question, then we can move on. Yeah, really interesting talk. I was curious, you showed what the database was for the infrastructure. What's the resolution of that versus the resolution of the model?
So this is where my project with NOAA right now is trying to expand this database. And what I use is there's been recent work to capture building height using synthetic capture radar. It also uses land schemes, and a lot of that is described in the first paper, where they do a continental what is building height. So that's the first level for building height. Then we also need to figure out, okay, in this land map, what is urban? And that comes from this huge effort called uWRF, where they do specific land classifications for the city. So they have 10 different levels. And those are, both of these sources are, the uWRF is 30 meters and the building is 1 kilometer. And my models are 4 kilometers, but I want to get lower to 1 kilometer. So that's later on.
All right, let's thank our speaker.